So let me do a quick review for last week. So last week we talked about defects and how defects is one great way for us to control the properties of materials. And we went through what vacancies are, what point defects are, substitutions, interstitials. And so I just want to do a quick review in terms of using the equation for finding defects. So if you have a cube, 1 meter of copper, and you heat it to 1,000 degrees Celsius, what is the number of vacancies that you would expect to find? Okay, so you have a cube of copper. You need to find out how many vacancies you might have at 1,000 degrees Celsius. Okay, so remember this equation that we went over last time. Okay, so I'm asking you to find this, right? Number of vacancies. And let me give you some things that you need to know. So the activation energy for copper, for vacancy in copper is 0.9 electron volts per atom. So what is the first thing you need to do if you want to know the number of vacancies? So this is the information you have. Do you have everything you need to know to find the number of vacancies, or do you need something else? If you think you have everything you need, then you could go ahead and calculate for n sub v. Yes?
What is that number?
What is this, right? Okay, so you don't know, so what does n stand for? Do you remember? What is that? Number of atomic sites, right? Atom sites. How many atoms do you have in this 1 cubic meter of copper? Okay, so you need to find that out. So how would you find that out? What would you need to find? So you know you have volume. The radius of the atom, right? But just knowing the radius of the atom doesn't necessarily tell you how many atoms you could fit within a 1 meter cubed, right? Because you don't know how closely packed those atoms are. I guess you could look up the crystal structure of copper. You'll have to find what the crystal structure might be at 1,000 degrees Celsius, and then use that to calculate the number of atomic sites. So we have volume, and we need to know how many atoms are in this volume. What is it?
We need to know the density.
Very good. Yes. So if you know the density, then you would know how much weight per volume copper has, and then you could convert the weight to the number of sites, right? Because you could convert weight to the number of atoms. Okay. So let me give you the density of copper at 1,000 degrees C is 8.4 grams per centimeter cubed. And then I'll also give you the atomic mass of copper so that you don't have to look it up. So please calculate N. Something that helps for me when when there's not an obvious equation to use is looking at units. Do that when you do equations. I look at how to convert my units from what I have to what I need. Right? So that's usually helpful for me. So the way I would approach it is I know I have these two numbers, and I see that I have grams per volume and then grams per mole. Right? So I could probably use those two numbers to find grams per mole. If I have grams per mole, then how would I be able to convert that to a number of atomic sites, you think? Well, actually, I would just have moles because the grams would cancel out, right? So I have volume to mole. So how would I convert moles to the number of sites? What is the connection there? Do you know any way to convert moles to sites, to number of atoms? Right, you have Avogadro's number. That tells you the number of what moles is to atoms, right? That's the definition of Avogadro's number, is the number of atoms in a mole. So what we have is we have 8.4 grams per centimeter cubed. And if you divide that by 63.5 grams per mole, the grams will cancel out. Now you have volume and mole, so you want to multiply by Avogadro's number, which is 6.02 times 10 to the 23 sites or atoms per mole. So the moles will cancel out, and that will give you sites per centimeter cubed. Okay? And so that's roughly 8 times 10 to the 22 sites per centimeter cubed. But we have a 1 meter cubed volume of copper, so we convert this to meter cubed. So sites per meter cubed. Is this the number that, did any of you get this number as well? 8 times 10 to the 28? Okay, all right. So now we could calculate for the number of vacancies. We have everything we need here. K, just a reminder, is 8.62 times 10 to the negative 5 EV per atom per degree Kelvin. Okay, so if you plug everything in, can somebody tell me what you get? What the number would be for N sub V? $1.53? Did you, for the temperature, did you use 1,000 as your number?
No, 1,000 and 200.
73, okay, you converted it to Kelvin. I got a slightly different number. So you got 1.53 times 10 to the 25. Per meter cubed. Okay. Did anyone get a different number? Mine's just slightly off, but I may have done my math wrong. Yeah. 2.2 times 10 to the 25. Okay, same units. Anyone else get a different number than these two? Right, we're just plugging in numbers. So this is the type of question, again, that I will expect you to be able to do on the exams. So if anything is unclear, please ask me now. We could go over it. Yes.
How we get the cube is
Where do you find the cube?
like
So usually it's given to you. Yeah, you wouldn't have to calculate it, so it's given to you here. And remember that there's a negative sign in the equation here, so it's negative 0.9 over kT. And T has to be in Kelvin, right? So 1,000 degrees Celsius is 1,273 degrees Kelvin. This is in. So I could take another poll. How many of you got this? How many of you got this one? More of you? And then anyone get a different number? Okay, so any questions about how to do this kind of calculation? All right. So roughly, if this is a number of vacancies we have, and this is a number of sites we have, okay, so roughly what percentage are we talking about? What percent of your copper cube is vacancies? Are we talking about a lot or a little? So number of vacancies divided by number of total sites. What number do you get? Anyone give me a number? What is this number divided by this number? I don't have a calculator on me. So if you just 2.2 times 10 to the 5, 25, divided by 8 times 10 to the 28, you get. And so V divided by N equals. Okay. And so if you were looking at percentage, you would move the, so what is the percentage of vacancies? Is it 27.5? Do you move the, to find percentage, do you move it this way too or this way too? To the right or to the left? Good way to figure that out is 100% is 1 over 1. So 1 is 100%, right? So 0.2. Okay. What is this number again? 2.75 -4. Okay. And so this would be 0.0275%. So that's what you would expect of a piece of copper at 1,000 degrees Celsius. A lot less than 1% of that volume would be made up of vacancies. Okay? Something important I want you to remember from this is that this is what is called a thermodynamically stable or equilibrium number. So this is what happens when you have a piece of copper, you put it in the furnace at 1,000 degrees C and you let it sit for a long time. And it has a chance to get to its equilibrium state. If you only put the copper in there for a minute, it really depends on how long it takes for these vacancies to occur, right? So it doesn't tell you anything about how fast this will be. It doesn't tell you the rate. This equation only tells you what will happen if you give it sufficient time. But it doesn't tell you how fast it will happen. So it might take a minute, it might take an hour, right? There's no units in here that has anything to do with time. Okay, so as a processing engineer, if you were to try to create the vacancies, you're missing a piece of information that's very, very important to you. Right? You know how many vacancies you can expect at the very end, but you don't know how long you have to wait. So that's something that we will talk about a little bit later after we finish talking about defects. And so last week we also mentioned that you have 3 different kinds of defects. You have point defects, you have vacancies, substitutions, and interstitials. And if you have 2 different kinds of atoms in a crystal structure, you form what is called a solid solution. So let's say a lot of you are looking at aluminum for your application materials, and you know that you could add other things, right? You have aluminum alloys. You can add different things into the aluminum, and so you can form a solid solution. So, a solution is when you have a liquid and you put sugar in it, the sugar dissolves into the water. You now have a water-sugar solution. If you just have sugar on the bottom of a cup and water on top of it, that's not a solution, right? Because they're not mixed together. A solid solution is the same concept. It's not 2 different materials sitting next to each other. The 2 elements are mixed together to form one phase. Okay, so it's 2 elements, 2 or more. So 2 or more elements that combine together to form a single phase or exist in the same crystal structure. And so how do you get a substitutional solid solution? What do you need in order to have 2 elements mixed together like this And this is something that's called the Hume-Rothery rules. So I don't expect you to memorize the Hume-Rothery rules for the rest of your life, but what's important is to recognize what is being represented in these rules and to remember if you were ever to think about forming a solid solution, you should look up these rules so that you know whether a substitutional solid solution can happen. So Hume-Rothery rules is for substitutional solid solutions, and especially for metals. So the Hume-Rothery rule says that if you want to form a substitutional solid solution, then the two elements that you're mixing together must be similar in size. So the difference in size should be less than 15%. They should have similar electronegativity. They must have the same, not just similar, same crystal structure, and similar valence. So similar number of valence electrons. So can you think of some reasons? Let's go over each of these rules, why you might need this rule in order to have a substitutional solid solution. Let's start with something really simple. You have a simple cubic. In a simple cubic, you have an atom on each corner, and this extends in 3 dimensions. To form a crystal structure. This is all one atom, so this is atom A. And you want to add atom B and form a solid solution. Why might them need to have similar size? Why is that a rule? Well, if I were to draw this in a 2-dimensional plane, it would look like this. Right? So if I were to draw this in 2-dimensionally, it would look something like this. So why would I need to have atoms of similar size if I were to form a substitutional solid solution? Right, so that the B atom can fit. So if I were to remove one of these A atoms to form a vacancy and insert a B atom into that vacancy, the vacancy site and the B atom needs to be at least similar for that atom to be stable within the structure, right? If it's too big, then it's going to push everything out. If it's too small, then it doesn't, the bonding distance is too great and it's not stable either, right? So it needs to be similar in size. The similar electronegativity and the similar valence is kind of the same as, because it tells you the kind of bonding it forms. Is it ionic? Is it covalent? Right? How many electrons does it share with its neighbors? So those have to be similar because it needs to be in the same kind of bonding situation with its neighbors. Okay, so rules number 2 and 3 has to do with the type of bonds, number of electrons is sharing or exchanging between the neighbors. Why does it need to have the same crystal structure, number 3? So if you had a B atom that by itself, let's say it's a BCC, why would that be a problem? Do you remember the number of nearest neighbors for a BCC? Or the number of atoms per unit cell, something like that. So back in the very beginning when we talked about unit cells and crystal structures, we talked about the number of nearest neighbors, right? How many atoms is touching? Okay. In a BCC, body-centered cubic, is touching, the body-centered atom is touching 8. How about here? This atom is touching how many? 1, 2, 3, 4, 5, 6, right? So in a simple cubic, you have 6 nearest neighbors. In a BCC, you have 8. In a FCC, you have another number. You should be able to figure that out. But in this case, if my B atom had a BCC unit cell structure, then it would be stable only if it had 6 nearest neighbors. That's why it forms the BCC. And BCC, they would need to have 8 nearest neighbors and would not be stable without 8 nearest neighbors. In a simple cubic, it will only have 6 nearest neighbors, and therefore it is not stable. Okay, so it needs to have the same crystal structure in order for the solid solution to be stable. So that's what the Hume-Rothery rules is telling us. All right. Any questions so far? Yes.
How about FCC and HC?
And HCP? Yes, so actually you're right, because they do have the same number of nearest neighbors in HCP, hexagonal closed packed, and face-centered cubic. So those two are, you can mix them. Very good observation. As long as the other things are, satisfy the other rules as well. Yep. So now I want to talk about the other kind of defects that can occur. The next kind is linear defects. So that's a line of atoms that are either out of position, well, basically out of position. And so let's imagine we have a crystal structure that looks something like this. Okay, and I want to draw. Okay, so it looks something like this. The lines just show you that they're directly on top and below each other. Okay, and if I were to insert a line of atoms here, what will happen is that I will end up with something like that. If I were. So I indicate that I have an extra row of atoms here with this line and then a little line below it to indicate that's where it ends, okay? This extra row. And then the atoms around it is distorted. And it's most distorted right around the dislocation. And it becomes less and less distorted as you go further away from the linear defect. And this linear defect is called a dislocation. So you can see that there's a zone around, so maybe it's like here. There's a zone around the dislocation where my atomic distances are not at the most ideal spacing, right? Things are a little squished or a little further apart. And so in this zone, I'm going to have a higher energy state compared to the rest of the crystal structure. Okay. So this is why dislocations are important. It disrupts the crystal structure. It creates a higher zone, a zone of higher energy. And we'll talk about later why that energy is important to know about. Okay. So you have two kinds of dislocations. You have what are called edge dislocations and screw dislocations. The edge is kind of like what I've drawn here. It's a row of atoms that are out of place, but it's sort of perpendicular to the direction of the atoms. So you just insert it. A screw dislocation is if you were to twist the material. So it would still be a row of atoms, but it would have an angle to it. So it would be, that's why it's called a screw dislocation. So whether it's directly inserted or if it's shifted in some way, those are the two types of linear defects that you can have in a material. But the main thing to remember is that dislocations create zones of higher energy within the material. And of course, dislocations can also be combined. It could be a combined edge/screw dislocation as well. Now, the next kind of defect, it's a planar defect. Okay, so it's a two-dimensional area where things are out of the ideal crystal structure locations. So the most easy to visualize kind of planar defect is a surface. Any material surface, you have a material like this, and you have atoms that are lined up underneath that surface in some way, some crystal structure, right? At the surface, that crystal structure ends. So surfaces are considered planar defects. So that all the atoms on the surface are not bonded in the ideal way. It is not in the ideal crystal structure because it's missing atoms on top. So again, because it's not in its ideal structure, it is not at the lowest energy state possible. It has a higher energy. And that's what contributes to surface tension, right? Materials, atoms on the surface have a higher energy state than the rest of the atom. And therefore, there is some energy on the surface. Okay, so that's surface tension. So if you have any material that's able to reorganize its own shape, it is going to try to minimize the amount of surface you have to the volume. And that's why water droplets are usually round instead of elongated way or triangle or some other shape. Because the sphere has the lowest surface to volume ratio. So if you were to calculate the volume of any shape and compare it to the surface, how much surface area it has, a sphere has the lowest surface to volume ratio. So that means if you allow any material to move its shape freely, usually liquids, then the higher the surface tension, the more likely it will form a sphere. The lower the surface tension, then it doesn't have the same driving force to minimize the surface tension, then it might spread out more evenly or easily. So you know things like mercury, which is a metal at room temperature but it's liquid, will form little spheres as well because it has a very high surface tension. Okay, so the surface is a defect. Another place where defects occur in a two-dimensional way is where two grains meet. So this is called a grain boundary. A grain boundary might look something like this. So you have your atom that's organized in this way here, but in a polycrystalline material, we know not every atom is organized exactly in a continuous way. We have grains where it's the same crystal structure, but oriented at slightly different angles. Something like this. So where these grains meet, this would be the grain boundary. Because you can see the atoms inside the grains still are surrounded by elements or other atoms that are in this ideal crystal structure, but the atoms right at the edge of this grain here, there's distortion, right? It's not in the ideal structure, so therefore it has higher energy at that place. Just go over one more thing, and that's volume defects. Another place is where phases meet, and that's called a phase boundary. Okay, so you can have, if one of these grains is actually a different phase, so not the same crystal structure, it actually is made out of a different crystal structure, then that would be a phase boundary instead of a grain boundary. So lastly, you have volume defects. And volume defects, as you can guess, is just a three-dimensional defect. So those can be a pore, so a hole inside the material, a crack, a cluster of impurities. So where the impurities are not forming a solid solution, but a little cluster of them embedded within your crystal structure. So the main thing to remember about all of these kinds of defects is that they create areas of higher energy. And we could use that, take advantage of that, manipulate that to change our material properties. And so tomorrow we will go over how do we figure out how many defects we have. We talked about that thermodynamically stable, we could calculate some things like the number of vacancies, but we don't actually know how fast that occurs, so we need more information. One, to observe the number of defects, and then two, to figure out how to add or remove defects, so we could actually manipulate material properties. So I'll see you tomorrow.